Hello everyone, I'm Ronak Banushali and I'll be presenting my work on person re-identification using Siamese networks. So, the task of person re-identification basically is to have a reference image and identify that person uh, in a different image. And the model that we use to do this has never seen any of those images before. So, let's see how it's done. This is the basic structure of any system that uses Siamese networks. So what Siamese networks are basically we use two uh, say similar looking feature extractors to get feature vectors from images. Now on top we see that we have a reference image of Baby Yoda. We get a feature vector from that image when we pass it through a feature extractor, and we have some candidate images at the bottom, so we get feature vectors for those when we pass them through the same network. And once we have all the feature vectors, we can compare them using some metric. In this case, for example, it's L2 norm. After L2 norm, we get the distance between the feature vectors, and depending on the distance we can identify whether the image belongs to the same person as the reference image or a different person. So in this case, Anakin has a higher distance because he is not Yoda, and the system seems to work. Alright, so the model architecture that we used is feature extractor, which uses convolution networks. So on the left we see a model architecture that is used for two of the models that I tested. So we have a batch of p times k images, where p is the number of people, the number of unique people in that batch, and k is the number of images per person. And once we have that, we pass it through a backbone, which could be ResNet 50 for the baseline or MobileNet v3 large, which is for the custom model. Once we get the features from the backbone, we apply global average pooling on the feature maps to get the feature vectors. Now these feature vectors are then used to calculate triplet loss and center loss during training as well as during inference. And then to speed up training, we apply batch norm on these features, and then we use those normalized feature vectors and pass them to a fully connected layer. Now the fully connected layer is of no use during inference because we have never seen the people that we are trying to re-identify. The only thing that we will have is a reference image. So why do we use this fully connected layer? Well, during training we know how many unique people there are in the given data set, so we can still use a fully connected layer at the end with the number of classes equal to those number of people, and try to find out the ID loss, which is basically just the cross entropy loss, and apply label smoothing on it. We'll get to discussing what ID loss, triplet loss, center loss, all these different types of losses are that we use here. So two of the models that I've used for this project are based on this architecture. The other model that I use for this project is OSNet, which is a model that is specifically designed for a person re-identification task. It is a very lightweight network that uses depth-wise convolution to speed up operations. The key difference in architecture for this model is that it uses multiple receptive fields by stacking the depth-wise convolution layers. So when we have multiple receptive fields, we get features which are at different scales. So basically we have smaller features as well as an idea of the overall structure and look of the image. So all of these feature maps are all of the outputs from these different receptive field convolution layers are then aggregated using the aggregation grades and combined with the input to form a residual block or a bottleneck, and this is kind of the specialty of this model. Now moving on to the training loss, one of the losses that we use is triplet loss. This is a quite unique kind of loss when it comes to person re-identification or any re-identification task. In triplet loss, we basically compare two feature vectors, and in triplet loss, we compare the feature vectors of an anchor, which is the feature vector of the reference image that we have, with the feature vector of a negative sample, which is not the person that is shown in the reference image. And we also compare the anchor with a positive sample, which is an image of the same person, maybe from a different angle or different view, but basically the same person in the batch. So what we try to do, as shown in the image on the top right, in a nutshell, we try to do some learning so that the distance between the anchor and the negative is maximized, and the distance between anchor and positive is minimized. So the loss function is max of 0 plus 0. Okay. The loss function is a maximum of, the loss function is defined as the max between 0 and the difference between the distance of the positive sample from anchor and the negative sample from anchor, plus a margin. Now this margin is to make sure that the negatives and the positives are separated by a certain gap. The higher the margin, the harder it will be to train the model, because it will try to push the positives and negatives far apart. Now, if the positive is closer to anchor than negative by a given margin, then the loss will basically be 0. So if that basically means if positive is close to the anchor, then you don't have a loss. That's how it should be. But if the positive is not closer to the anchor and the negative is closer to the anchor, then we have a loss that is greater than 0. Now these are some of the other techniques that I used to make sure that we have a good loss metric. Now these are some of the other techniques and losses that we use for ReID. The first one is center loss. Center loss penalizes the model if the feature vectors for the same ID look different. So basically what that means is, let's say for a given positive sample, the distance between positive and anchor is 0.3, and the distance between the negative and the anchor is 0.7, and the margin is 0.3. Well, the loss in this case is 0. However, if we have a case where the distance between the positive and the anchor is 1.3 and the distance between negative and anchor is 1.7, we still have the positive closer to the anchor by a given margin. However, the distance is more than the previous negative. So in this case, even though the relative distance is less for the positive than for the negative, the absolute distance is still a bit high. So what this does is basically compare feature vector for the same class against a center feature vector, which is basically a mean or an average feature vector. So that's what we get when we take the norm of the feature vector and subtract the center from it, and that's how we calculate the center loss. Now this helps to keep all the feature vectors of a same ID close to each other in feature space. Other technique that we use to make sure that we have good loss metric is label smoothing. Now ID loss is the loss that we get at the end of the fully connected layer. It is basically cross entropy loss or any loss that we use after a fully connected layer. Now we apply label smoothing on it, which is a way to make sure that the model doesn't overfit or isn't too confident. So instead of giving the ground truth during training as 1 for the correct class, we give the ground truth to be 0.9 and distribute the remaining 0.1 probability among all the other classes. This makes sure that the model is robust and doesn't too confident. Another technique that we use is hard negatives. So we try to find the hard negatives during training. Now, in the image on the right side, if we assume that the anchor lies at the center, and the first inner circle is where a positive sample lies, then any negative sample that lies within that circle would be considered a hard negative. So what this means is, in a given batch, instead of randomly picking for a negative sample for a given anchor, we would specifically look for the negative sample that is closest to the given anchor. It is possible that that negative sample would be closer than some of the positives, which would result in a higher triplet loss, as we saw in the previous slides. So this makes sure that we have a good value for loss, and if we rely on random sampling, then it's possible that we get loss as 0 a lot of times when that is not the case. In the end, we combine all the losses by the formula given at the bottom, which is ID loss plus triplet loss plus beta times center loss. Beta is a control hyperparameter, and it can be tuned to get the best performance. Now, moving on to the datasets, we have 3 datasets that we used for this project: the market dataset, Duke dataset, and last dataset. It is all of these datasets are standard and used widely for benchmarking. The market dataset has 1500 IDs and 31,000 images and has 6 different camera angles. The Duke dataset has 702 IDs with 16,000 images and 8 camera views. And the last dataset is made from movies, so it doesn't have camera angles as such, but it is a huge dataset, and people of the same ID even change clothes and appearance. So it is a hard dataset to train on. It is not easy to train on the last dataset. So these are some of the results. We have the CMC plots for all the datasets and all the models, and we see right away that for market and Duke, the models seem to train pretty well, with almost 90% rank 1 accuracy. The baseline does pretty well for market, and it does really well for Duke as well, but it's hard to train on last. It doesn't train really good on last. OSNet is surprisingly good for how lightweight it is, and it doesn't even use a standard backbone. So OSNet is the best when it comes to computation and performance. So, and the custom model that we chose is close to OSNet in most of the cases, but at the same time, it seems to have more parameters. So the baseline has 24 million parameters because it uses ResNet. Meanwhile, OSNet has 2 million parameters and the custom model has 6 million parameters. The feature vector for the baseline is 2048 elements long. For OSNet, it's 1000 and custom model is 960. The conclusions from this project are that the suggested baseline is pretty good, but OSNet is the best overall pick because it's neck to neck with the baseline. The MobileNet is fairly lightweight and does okay, but it's not the best for ReID, and it is possible that the feature vectors that it produces are not optimal for the ReID task. It should be kept in mind that OSNet was designed specifically for the ReID task, and different distance metrics were used, and most of them gave the same results. However, since there was no time to train with the different distance metrics and they were only tried for the inference part, this experiment regarding the distance metric was inconclusive. Transfer learning worked well when we tried to continue training on a different data set with pre-trained weights from another data set, and it starts to converge really soon. So it works well from dataset to dataset, at least between Duke and Market. But considering that the overall performance for all models was bad for the last dataset, transfer learning had similar performance. So it's safe to say that transfer learning worked really well between datasets. Yeah, thank you.